All right, let's finish up a few ideas about the basic matrix operations. And just to recap where we were already, we introduced the idea of adding matrices and multiplying matrices by a scalar. And this was Theorem 1, kind of summarizes what you can expect from doing that. Then we talked about multiplying a matrix by another matrix. We looked at two different ways to do it computationally. And then we didn't actually look at this, but Theorem 2 says there are some things that you can expect from matrix multiplication as well. So here they're saying suppose A is an n by n and B and C are the right sizes, so you can do the multiplications. Then they say, you know, association still works. If you've got A times BC, you can do BC first, or you can do AB first, and you'll get the same result. They say distribution works. If you've got A times parentheses B plus C, it is the same as A times B plus A times C. That's distribution. And notice they have left distribution and they have right distribution. You're like, why do they have two separate versions? Because remember that multiplication is not commutative. Multiplying one way and multiplying the other way don't necessarily give the same answer. And they won't here either, but both directions you can distribute. D says you can also multiply a scalar in different places, and actually they could have even had another version that says A times B first and then an R on the end. And then an identity matrix times A, you can multiply that. That's one of the rare exceptions to the rule where multiplying by 1, or the matrix version of 1, is commutative, the identity. If you don't remember the identity, keep in mind that an identity matrix is something like, for a 2 by 2 at least, it would look like that. It just has zeros everywhere except 1s on the main diagonal, which basically says take 1 of the first column and make that your first column, and take 1 of the second column, make that your second column, right? That's why it gives you that same thing. Okay, so the place that we finished off was by saying that matrix multiplication is not commutative, so it's not necessarily true that A times B will equal B times A, which means there's a couple other moves that we like from our basic algebra days that you're going to have to break yourself of the habit. I think one thing that we're very used to from basic algebra, anywhere else in algebra, if this was true, if A times B equaled A times C, you could cancel. And this would be a proof that whatever B was is the same thing as whatever C is. Not necessarily the case here. And I am not trusting myself tonight to do any more matrix multiplications by hand. So I am going to let the calculator do them. So let's take a look at this matrix times this matrix. That result comes out negative 21, negative 2177. So I'm going to go back, I'm going to do the first one again. But this time I'm going to do it, times. This time I'm going to do it times this one. And notice that's also negative 21, negative 2177. I have two different products here. 3, negative 6, negative 1, 2 times this matrix. 3, negative 6, negative 1, 2 times that matrix. The results are the same, but obviously if you sort of cancel the 3, negative 6, negative 1, 2's, these aren't the same matrix over here. So it's definitely not true that you can sort of cancel on both sides. Another sort of fundamental basic algebra technique. This is why factoring works. It's to say if you've got two things multiplied and you get 0 as a result, in basic algebra, you would say that means either A had to be 0 or B had to be 0. That's why you take like quadratic equations and you set them equal to 0. So you can then factor and say one of those factors must have been 0. That is not necessarily true here. If you multiply two matrices together and get a 0 matrix, doesn't necessarily mean that either one of them was 0 to start with. Let's look at a counter example there as well. Let me come back to my very first matrix, the 3, -1, -6, 2, and I am going to come up with the matrix on my own here. Let's get another 2 by 2 matrix. Keep in mind the sort of vector by vector version of matrix multiplication, the first one that we looked at. And notice my columns here. I've got 3, -1, and -6, 2. It looks like if I did 2 of the first column and 1 of the second column, those would add to 0, 0. And likewise, I could use 2, 1 again for that matter, but I'm going to not repeat myself. And let's say if I did 4 of the first column and 2 of the second column, that should also give me a 0, 0 result. So yeah, there I can multiply those two non-zero matrices together and get an all 0 result. So there's another sort of basic algebra move that doesn't work for us. So really 3 basic algebra moves. The third one just being that this doesn't work. So not commutative, can't cancel, can't use the 0 property of factoring. Okay, so I just want to introduce one more matrix operation to you. And if you were watching closely when I used my calculator here, Microsoft Mathematics always, anytime you do a matrix calculation, it says, hey, maybe you also want to do a few other things. Reduce is one that we already know about. Size would just tell you it's a 2 by 2 or a 5 by 7 or whatever. Transpose, we don't know, and that's the one we're going to look at right now. Trace and inverse and determinant we're all going to look at later. But for the moment, let's talk about transpose. Okay, so let's talk about transpose. Of a matrix. The basic idea of a transpose is to turn rows into columns. It's a pretty basic idea, and we're not going to do a whole lot with it, but it's useful notation for the times that we do want to do this. So let me just say that the basic example. So there's a matrix, and the transpose, they sort of write it like an exponent, even though it's not an exponent. But the transpose of that matrix would be the first row, 3, 2, 4, becomes the first column, 3, 2, 4. And the second row becomes the second column. Ta-da! You've done transpose. You know a new matrix operation. Congratulations. Yeah, really that's about all there is to it. You can transpose a matrix of any size. I did a 2 by 3 just to sort of make it a little more clear, but you can certainly do it on a square matrix. You transpose a 2 by 2, it's still first row becomes first column, second row becomes second column. So they have a couple things they would like you to know about this new operation of transpose. They would like you to know that if you transpose a matrix and then transpose it again, you get back to where you started. Hopefully that makes sense intuitively. If you turn rows to columns and then turn the columns back into rows, you should be back where you started. For addition, transpose distributes. You can add the matrix first and then move rows to columns, or you can move rows to columns first and then add, and you'll get the same thing. Also true that you can do scalar multiplication and then transpose, or transpose and then do scalar multiplication. Either way, the rows are getting flipped for columns, and every entry in the matrix is getting multiplied by 5 or something, right? I think A, B, and C are pretty intuitive as you think through what we're talking about. D is a little less intuitive. It says if you have two matrices multiplied, and again, here's where things are a little bit different than what we're used to with matrix multiplication. If you multiply two matrices and then take the transpose, that's the same as taking the two transposes separately first and multiplying in the opposite order. I'm not going to prove that right here. I'm just going to point it out. I will just say that if it was in the same order, like if you were trying to do A transpose, B transpose, probably the dimensions wouldn't even match. Right? When you flip rows for columns, then you probably don't have the right number of columns to match the rows here anymore. But it does work in the opposite order. So I think that's all that I wanted to say. Again, any good matrix calculator will be able to do a transpose along with anything else. I find transposes are often easier to do by hand than they are to type into a calculator. It takes a lot of time to type those things in. But with those, you should be set. Oh, I did want to mention one more thing. Let me get one more thing on here. Since I mentioned that transpose looks like an exponent, they are going to start doing exponents. I actually don't know if they do one in 2.1, but it's coming soon if we don't get one here. And I just want to point out that this is the definition of an exponent, just like it always is, which is repeated multiplication. That would mean you would do 1, 2, 3, 4 times itself 3 times. This actually has a lot of use if you think back to our section on applications where we were looking at the Leon-Tiff input-output model. This would be like 3 years or 3 cycles. So you can sort of predict what's going to happen over the long run. And the same thing for any other transition matrix. Right? This will predict long-term behavior. Which means later in the course we're going to want some efficient ways to compute large powers of matrices. But that's a topic for another day. Okay, I'll let you get started on the homework. Again, the idea here in the homework is just to get comfortable with the basics of matrix operations. So try to do these by hand. Check yourself with a calculator. And then after this section, I'll say, hey, if it's all numbers, do it on a calculator. If it's numbers and letters, obviously, then you'll have the idea locked into your brain because you did this section by hand. All right, have fun with the homework.